Good morning. I'm very happy to introduce Dr. Manel Prada. He obtained his PhD in marine geophysics in 2014 in marine geophysics. So then he went to Dublin for a 5 years postdoc. In 2019, he won a Beatriu de Pinós postdoc grant in the ICM, in the Marine Geophysics and the Marine Science Institute. And since 2021, he has a permanent position as a researcher in the Barcelona CSI and the Department of Geosciences. So his research interest is focused on the two most important processes in plate tectonics, so seafloor spreading and also subduction zones. And more recently, in the factors that controls the processes involved in the Megathrust earthquakes. Megathrust earthquakes are the biggest earthquakes on Earth. So he's a specialist in geophysical data, but mainly in seismic data, gravity data, also bathymetric data. And he's a very specialist, and he encompasses all of the process in the publication of a paper. He goes to the sea, he makes the acquisition, the processing of the data, the interpretation, also the modeling, and finally he's able to write a paper. So thank you, Manel. I'm very happy to introduce Manel. He's a friend of mine. We pass a lot of days at sea, so I pass the word to you. Happy to...
Thanks. Thank you, Rafa. And thank you, everyone, for being here. So, as Rafa said, I'm going to be talking about subduction zones and megathrust earthquakes, as you can see in the title. But what are subduction zones and megathrust earthquakes? I will start with this image over here, which is basically a seismic section that shows the structure of a subduction zone right at the beginning of the process, where we can actually see the lower plate over here, the upper plate, and the plate interface shown by this red line. So megathrust earthquakes are large earthquakes that occur at the plate interface, and they are quite dangerous because they release a lot of energy. They can trigger tsunamis, so it's a natural hazard that we need to take into account to actually mitigate coastal hazards. So this is the outline of my talk. I'll be talking about subduction zones and megathrust earthquakes, why they occur. And then I will jump into a more detailed discussion on the key factors that control the propagation of megathrust earthquakes and their dynamics. I'm presenting these 3 studies over here. The last one is still work in progress. And I will finish with just a hint on what we know about the 3D structure of a subduction zone. So what are subduction zones? Subduction zones are part of plate tectonics, and therefore they are included in the Wilson cycle. The Wilson cycle describes the evolution of the Earth's surface and the plate tectonics from continental collision, rifting, seafloor spreading, and the birth of new plate tectonics. And finally, the subduction zone is the destructive plate boundary, where the tectonic plate becomes subducted, and the oceanic plate, the tectonic plate of the ocean becomes recycled deep into the mantle. Now, when this happens, we have the mid-ocean ridge here and the subduction. 2 large tectonic forces come at play. The first one is called ridge push, which basically pushes the lithosphere, the plate, towards the margin. It creates convergence, and eventually subduction occurs. And when this occurs, another tectonic force called slab pull appears, and these 2 tectonic forces maintain this whole process going on until collision occurs with the next continent that collides with this structure over here. So subduction zones are destructive plate boundaries. They are regions where oceanic lithosphere is recycled deep into the ocean. And with that, we have that oceanic rocks and pelagic sediments, all rich in water and carbon, are actually recycled deep into the mantle. So subduction zones are key in the water and carbon cycle of Earth, so they are important also for this in this site, in that regard. So, but they are also important because of these large tectonic forces and the geochemical reactions that this water and carbon trigger when they subduct. They are a hotspot for natural hazards, namely earthquakes, submarine landslides, tsunamis, upper plate volcanism. And I'm going to be focusing on the main one. And this is better depicted in this animation, which shows the recording of earthquakes since the 50s. And what you can see is that the largest circles, which are, they basically depict the magnitude of the earthquakes, so the largest magnitude earthquakes occur along this region over here, which is called the Ring of Fire. And this region is the result of the subduction of large oceanic plates in the Pacific beneath the surrounding continental plates. So why megathrust earthquakes occur in these regions? So the basic process is basically that we have an oceanic plate downgoing continuously, and then the upper plate becomes stuck in this region over here and starts storing elastic energy until the tectonic force of the upper plate overcomes this friction. Then an earthquake happens and releasing all this elastic energy in the form of an earthquake. So this is better depicted in this diagram, where the hand over here would be this slab pull force that is actually pulling continuously the oceanic plate, and then the spring and block system would actually represent this stick-slip behavior of the upper plate and the sudden release of energy in the shape of an earthquake. Now, of course, when these earthquakes reach the shallowmost region of the upper plate, they actually they trigger a sudden deformation of the seafloor, and therefore a sudden perturbation of the water column, which triggers a devastating tsunami, such as the one that we have seen in Tohoku in Japan, that we have a picture over here. So these earthquakes are, we need to understand how these earthquakes propagate and how these earthquakes release so much energy in this region. What are the reasons for that sudden release of energy, in order to prepare, in order to kind of like mitigate the impact of this, predict the impact that this earthquake could actually create in the coast and mitigate the disaster. So one of the key aspects controlling this, the propagation of these earthquakes is basically the structure of this upper plate. And what I will start talking about is about the elastic properties of the upper plate, which are, as you will see, are basically determining how these earthquakes propagate. Now, this is the view that we had in 2012, probably earlier, about the Megathrust fault. We have a region over here in terms of seismogenesis, so in terms of how earthquakes are distributed in this interface. What we see is that there's a region which is confined between 10, 15 kilometers and 30, 50 kilometers of depth, where the earthquakes occur and nucleate and propagate, okay? Now there's another region, a shallow region called aseismic. Aseismic means that it won't release seismic energy, where a particular class of earthquakes called tsunami earthquakes rarely occur in this region. And when these earthquakes occur, they actually they had larger slip, so larger fall displacement, slower rupture velocity, they propagated slowly, and moderate shaking compared to earthquakes that occur in this region over here. So what at that time was actually thought is that this behavior over here was exclusive of this particular class of earthquakes, the tsunami earthquakes. Now, with the occurrence of larger earthquakes, such as the Tohoku or the Sumatra Andaman, that nucleated in this region and propagated all the way up to the trench, we saw that these characteristics are not only particular from these events, but from all the earthquakes that propagate through this area. So, for example, the Tohoku earthquake actually displayed moderate shaking, larger slip, and a slow rupture velocity in this when it reached the shallowmost part of the megathrust. So this behavior is not exclusive only of tsunami earthquakes, but from all earthquakes that reach this shallow portion. Why? Well, there are many reasons that were proposed. particularly site-specific factors such as a weak subducting sediment interface, the presence of pore pressure variations along the plate interface, or a depth dependence of initial stresses along the fold. But the problem is that none of these arguments could explain the whole ensemble of arguments defining this depth-dependent behavior of dynamic properties. Until this study came up in 2019, presented by Valentia and Cesar, both from ICM, in which they proposed that the dynamic behavior of these megathrust earthquakes is mostly explained by the variation of elastic properties at the base of the upper plate. Now, this hypothesis is based on the fact that when we are in this interseismic cycle, so in between the loading of so when we are loading elastic energy and before the release of the earthquake, most of the energy, most of the elastic energy is actually stored at the base of this upper plate, okay? So what they did is something that we can't do with fold friction. So we don't really know what fold friction is in situ, but we can actually assess the distribution of elastic properties from tomographic models. So they compile information from all over the world, from different subduction zones, and they integrate, and they create this distribution. They observe that the distribution of elastic properties following this region over here above the interplate follows a global trend, which basically is reflecting variations in depth in the tectonic signature of the upper plate. So based on this, they come up with this model in which the shallow domain where elastic properties are quite low, in this case rigidity, which is what I'm showing here, is representative of a media with a lot of fracturing. Now we have the transitional domain with these fractures are become less and less observed because of compaction. And in the end, we are in this regular domain where lithostatic pressure is really high, and therefore we could assume that we have an intact rock with very little fracturing. So with this distribution over here, with these values of rigidity and this distribution, one can calculate relative values of slip between the deepest portion of the megathrust and the shallowmost portion. And this is what they did. They actually used this distribution of rigidity to calculate slip ratio between the deepest portion of the megathrust and the shallowmost region. And they did the same for rupture duration, for the time of propagation of the earthquake, and for the frequency content of the earthquake. And what they show in these diagrams, I won't get into much detail into this, but what they show is that the same earthquake, for an earthquake with the same magnitude occurring at this depth and at this depth, what we will see is that the slip will increase tenfold if the earthquake travels through the shallow domain rather than in the regular domain. And this is because the elastic properties are much lower in this media than in the deeper portion. The same happens with the rupture time. For the same magnitude earthquake, if this earthquake propagates through the shallow domain, we will get that the duration is almost 3 times larger than if the same earthquake propagates through the deepest portion. And then there is also a frequency variation with depth that basically explains the fact that shallow earthquakes have a moderate shaking as compared to deeper earthquakes that have more higher frequency shaking during the propagation. Now, this conceptual model basically explains all the depth varying behavior of megathrust earthquakes with a global depth variation of upper plate elastic properties. But what does this mean? This basically means that the tectonic signature of the upper plate controls to a great extent the dynamics of megathrust earthquakes. Therefore, we need to understand the structure of the upper plate if we want to predict the dynamic behavior that a potential megathrust earthquake would have in the megathrust. We actually, after this conceptual model was presented, we used numerical simulations to actually validate this conceptual idea. We use a numerical rupture dynamic simulation tool that takes into account 2 ingredients. The first one is the elastic properties of the media, And the second one is the fold friction. And as I said, fold friction is quite uncertain. Many studies, what they do is to assume a range of values based on empirical observations. But what we did here is to assume the same frictional behavior for all the tests, but we tested different medias and we compared them. So the results basically isolate the effect of the elastic media and not the friction of the fold. And what we found is that using this distribution, which comes from the previous study, from the conceptual model, is that we were able to reproduce with this red line the values that this conceptual model presented in the previous paper. So we kind of validated the conceptual idea that rigidity and elastic properties control these dynamics of these earthquakes with numerical simulations. Now, I'm going to start showing you some studies, some case studies in which we applied this conceptual model, this idea, to explain the dynamics of real events. The first one is the 1992 Nicaragua tsunami earthquake. As you can see, this earthquake is a tsunami earthquake, so it nucleated very shallow. So this is Nicaragua. This is the Middle American Trench over here. This is the oceanic plate. This is the upper plate over here. And the star depicts the nucleation of the earthquake. So you can see that it's very close to the trench. It nucleated at 10 kilometers depth, which is very shallow for an earthquake, a megathrust earthquake. And therefore, it actually released a large fault displacement in this area. It was characterized by anomalous long duration and disproportionately large tsunami for the moderate shaking that had at that moment. No? So the idea is to try to explain all these aspects with observations with observations from geophysical information about the elastic media through which this earthquake has been propagated. So we actually took these three lines over here. We performed a travel time tomography, and we extracted the distribution of, in this case, this is P wave velocity, what I'm showing. So we extracted the P wave velocity of the upper plate for three lines and the geometry of the megathrust over here, and we created a surface model over here that basically was representative for the distribution of elastic properties above the megathrust. So we took this information and we combined it with seismological recordings of the 1992 Nicaragua earthquake. That I didn't say that, but this event over here was actually recorded, was instrumentally recorded, so we could actually use this information to derive, invert dynamic properties of the earthquake, such as slip and seismic moment. So basically what we found is that we were able to explain with the combination of these two informations, the upper plate elastic structure and the wave field of the earthquake, we were able to calculate the slip distribution, rupture duration, and seismic moment. And in summary, the results explain the large slip near the trench, the shallow duration, the slow duration of the earthquake, and the moderate shaking of the event. Now, I'm going to jump now to another study over here, in this case in Mexico, offshore Mexico. This is a paper we published recently with Rafa and co-authors. And in this case, what we want to explain is the dynamics and the occurrence of this earthquake, the 1985 Colima-Jalisco earthquake. Now, this event occurred in this portion of the margin, okay? We are in this area where the Ribera plate, the Ribera oceanic plate, is actually subducting beneath the North American plate. And this region is characterized, the margin is characterized by the occurrence of three large megathrust earthquakes of magnitude 8. And the problem here is that the structure of the margin is quite unknown because of the lack of geophysical information. So in particular, this is 1995, not 85. The 1995, it basically generated a tsunami with tsunami waves up to 6 meters in some regions, such as the Bay of Manzanillo, and the most let's say, interesting thing is that this earthquake actually released 1/3 of its energy near the trench, even though it was nucleated at 20 kilometers of depth. So now we are in the case of, like, this would be more or less like a tsunami earthquake, but with the difference that it was nucleated much deeper. So many authors actually discuss the dynamics of this earthquake as a tsunami earthquake, but it has never been classified as such because of the deepest nucleation. Now, the reasons for such large slip and the occurrence of such slip in the shallowmost part of the trench, of the fault, they have been speculated some ideas, but the problem is that no images of the margin were present before, so nobody knew the mechanism behind this tsunamigenic event. Until 2014, where we did a seismic survey, bathymetric survey, and well, we acquired several geophysical data sets in this region over here. In particular, what I'm going to focus is along this line, TS02, which samples the structure of the margin in the area of the 1995 Colima-Jalisco earthquake over here. What you see with contour lines is the slip values of the event, and the star is the nucleation of the earthquake. So what we can see here is are already some interesting features in the bathymetry, for example, that I would like to highlight. For instance, in the northern part of the Rivera Plate, the seafloor is quite smooth. It's quite flat, let's say, with the exception of little seamount chains that are actually quite visible in the bathymetry. The rest is quite smooth. While if we go to the south, the bathymetry becomes rougher, and actually we can see that in here. And this has an impact on the margin. So if we go to the north, we have an accretionary margin where all the sediments get stuck and accumulated and packed as the subduction occurs. Whereas in this region, depicted by this continuous yellow line, the margin is highly eroded. So there's a process that is actually kind of like removing material from the margin and kind of like destroying it. Now, the results along this line are quite interesting. So we actually perform first travel time tomography. We come up with a velocity model, and then we migrate the seismic section in depth. This is depth over here. Usually these sections are presented in time, but we perform an extra step in the processing sequence to come up with this image. And what we can see, what I would like to highlight is the geometry of the interplate has actually some topographic variations over here. And I would like to highlight this height over here, which is basically associated with a lot of fracturing atop of this ridge. Now, if we combine this information with the velocities, we actually see that these contour lines are velocities, p-wave velocity. We see that this fracturing is actually related with low velocities, so possibly fluids over here. And what you see in red is the inverted interplate, which coincides quite well with what we see in the MCS section. So what we are observing here is a topographic anomaly at the interplate that is subducting and is damaging the upper plate structure. Now the question is, what are we imaging in here? How do we interpret this topographic anomaly? Now, there are tons of studies that have actually imaged the presence of subducted seamounts, so large mountains, submarine mountains that get into the subduction, and they basically uplift the upper plate, and they leave a trail of fractures as this mountain is passing by with the subduction of the oceanic plate. The problem with that is that the subduction of seamounts, as you can see here, this is a picture of Costa Rica, and what we see here, this is the trench, this is the oceanic plate, and this is the continental plate, so the subduction occurs in that sense. What we see is that these large mountain, large seamounts, they leave a localized trail of deformation. So it's not widespread along the margin, but they just leave portions of erosion like this one, these little embayments in which they actually, that basically reflect the path of the seamount as it was subducted. Now the difference with our region is that the pattern of erosion is widespread along the margin, and no clear embayments are actually observed in the margin. Rather, we actually see that the margin is eroded similarly along the trench, which is, let's say, it's in contrast with the presence of a localized topographic anomaly. And the fact that we don't actually see a localized seamount change in front of the margin, and the fact that some of these large ridges over here are topographically alike to what we have inverted. What you can see here, these are topographic profiles extracted along this region over here, and compare with this red line, which is the inverted topographic anomaly that we obtain along the margin, beneath this portion of the margin. So our interpretation is that what we are actually imaging here is an elongated feature similar to what we see in the oceanic side of the bathymetry. Therefore, this has implications for the coupling of the plate, as we will see now. Now, there are many studies that talk about these implications, how this subduction of rough topography would impact in the friction of the upper plate with the downgoing plate. And in summary, what they show is that in the leading flank of this topographic anomaly, overpressure builds up, which would promote the occurrence of confined earthquakes and confined ruptures. Now, interestingly, there are other studies that show that the rupture associated with these topographic anomalies is controlled by the spatial extent and shape of these subducting features. What you see over here is just a slip distribution of an earthquake that occurs along a flat interface with no topographic anomaly. And you can see that is actually evenly distributed. And whereas when we actually have topographic anomalies, this distribution is kind of like focalized in this topographic roughness, no? Like in these squares over here would represent the presence of localized seamounts, okay? So the idea here is that our interpretation is that if we have an elongated trench parallel ridge that is causing overpressure, what we should see based on these observations is actually an elongated trench parallel pattern of asperities, so of regions of high pressure. Now, if we go back to the slip distribution of the 1995 earthquake, we actually see that in the shallowmost part, the slip distribution is actually trench parallel and not focalized in one single place, as it would occur in the case of a localized seamount. So this is kind of supporting the idea that we have a bunch of trench parallel ridges that are actually kind of like overpressuring the upper plate, and in some cases, such as this earthquake, may assist deeper earthquakes to rupture up to the trench. Now, these arguments explain why a deep earthquake actually propagated so close to the trench, but they don't explain why they released so much energy and why it was so slow. Now, these are the two, let's say, dynamic aspects that we know. So the two aspects related to the dynamics of these earthquakes that we know, that it released large slip and it was very slow in this part. So what we are going to do is going back to this conceptual model where rigidity and elastic properties explain these dynamics. We are going to see if our observations can actually explain these aspects. Now, I just want you to bear in mind this value, which is the rupture velocity that has been estimated for the shallowmost part, which is between 1.5 and 1 kilometers per second, depends on the study. So the first one that I want to show is the classic rigidity versus upper plate thickness, which is similar to what Valentia and Cesar presented in their study. And what you can see is that the gray dots are the values from our tomographic line, and they actually coincide quite nicely with the global trend presented in this paper, which was expected. But if we plot the rigidity instead of upper plate thickness, we plot it versus distance from the trench, and we plot the relative topography of the plate interface, we actually see that these large topographic anomalies actually are causing localized areas of low rigidity in the upper plate. So low rigidity in this area, in particular, is associated to the rich subduction. And as we have seen in previous studies, the low rigidity of the upper plate promotes large slip in the shallowmost part in the case of a shallow earthquake. Now, the last aspect that is still there is the rupture velocity. So we know that the rupture velocity varies in between 70 and 90% of the shear wave speed, which is what I'm plotting over here. This is Vs. With the circles, and in gray I'm showing the rupture velocity, and if I calculate the average in this in the shallowmost part of the plate in the first 12 kilometers to be consistent with the shape of the models that have calculated the velocities, what I actually found is that this velocity is the average velocity is close to 1.5 kilometers per second, which is consistent with finite fold inversions of the same earthquake. So our observations can explain not only the occurrence of this large earthquake near the trench, but also some of the dynamics of this event. Now, the last earthquake that I want to elucidate here is the 2011 Tohoku-Oki earthquake. This is the last study that I'm presenting over here. This is a very well-known earthquake, and it released a lot of energy near the trench. There's a large uncertainty regarding the values of slip, as we will see now. But the values kind of like vary between 50, 70 meters fold displacement. And because of this large displacement near the trench, as we've seen in the animation before, a large tsunami was actually triggered. And it was quite quite disastrous for the coastal populations. Now, even though it's been well studied, what I'm showing here are 32 finite fold models of the earthquake. So this is showing the potential fold displacement that the same earthquake had at that moment, and you can see that there are a lot of variations in here. So another thing that is still under debate is why. But I mean, what I want to show here is that even though they are different, most of them, they are actually showing that it released a lot of energy near the trench. But until now, we don't really know how this earthquake could actually reach that portion of the fault. Like, what are the factors controlling this shallow propagation? No? So what I'm going to do here is to extract elastic properties along the media, along this section over here, which is crossing the area of highest fold displacement. There is a tomographic image over here, so I'm using these velocities to extract BP, VS, density, and rigidity. And also, what I'm using here is friction information. So in few places in the world, we actually know what are the state of friction in the fold. And one of the places is here in Tohoku, in Japan, where an IODP expedition occurred in 2012, and they actually drilled the upper plate, and they reached the plate boundary over here, and they extracted information regarding fault mechanics, rock physics, and so on. So what I'm showing here is what they found is that the plate boundary is actually represented by clays that are actually representing the plate boundary, and these clays are actually exhibit a low coefficient of friction, as you can see in this panel over here. These are different samples from different regions of the world, and this is the Japan trench, showing how this these samples from the fault zone exhibit a low coefficient of friction, meaning that they are very weak. So these authors, what they said is that the fault is so weak that when this large earthquake arrived, most of the energy was actually canalized along the fault plane. And very little energy was scattered away from the fault, so very little off-fault deformation occurred, which actually allowed the fault to canalize a lot of energy and break into the trench. The problem with that is that if you look at the simulations that they've done with this earthquake, is that if we assume this weakness and we assume a realistic distribution of elastic properties, which is what I'm showing over here. This is the upper plate with this tomographic model over here, showing the presence of a low velocity, low rigidity and sedimentary prism over here. And we assume the weakness of the fault. What we get is unrealistic values of fault displacement in this area. Okay, what you see over here, this is distance from the trench. This is a slip, so fault displacement. And in dashed lines, what you see is the reference slip curve. So this is an average of the slip curves from many studies. So basically, let's say that the highest slip, the average slip in the trench should not be higher than maybe 40, 50 meters. But what we obtain is like fault displacements of 500 meters if we assume this scenario, which is not realistic at all. So there must be something else at play in here that explains this slip pattern with this elastic media. Now we know that during the earthquake there is off-fault deformation, and this off-fault deformation, this plasticity, depends on the plasticity of the upper plate, and this plasticity is a function of the rigidity. Now, what you see over here is an example of a simulation that considers a strong material with very low plasticity, so almost no off-fault deformation. And what you see over here is that the uplift of the seafloor, which is a proxy for how much slip there is in the fault, actually peaks at the trench. So there's no uplift, widespread uplift in the upper plate, but just localized in this area, because in this area, what happens is that the slip peaks and with unrealistic values. But if we consider a weaker material, so a more realistic structure of the upper plate, what we see is that the slip is not focalized in the shallow-most part, but is actually distributed, and the uplift is actually widespread all over the upper plate, mimicking a more realistic deformation pattern of the upper plate. So the idea here is that we know that there is a weak accretionary prism over here with very low velocity and low rigidity that spans for 20 kilometers along the fault. So the idea is to consider a simulation that takes into account this rigidity-dependent plasticity in order to explain, to actually evaluate the role of this structure in the dynamics of the earthquake. Now, what I'm trying to emphasize here is that not only the elastic properties above the fault matter, but also the elastic properties all over the upper plate, which basically define how this plate will behave during the shaking of the earthquake. Now, finally, I just want to show you these last results that we obtained offshore Ecuador. So we have seen so far that there is a global trend of elastic properties, but we've seen little differences between subduction zones. Now, what I want to show you here is that these differences are not only between subduction zones, but within the same subduction zone. Now, what we see over here, what I'm going to show you here is just a tomographic image of the subduction zone offshore Ecuador over here. Red dots are ocean bottom seismometers, and black lines are shooting lines. So what I'm showing you, this is the perspective over here. This are different slices at different depths of the tomographic model, showing P-wave velocity information. The upper plate is here, and you can actually see not only down deep variations, but also along strike variations. This is the geometry of the megathrust of the interplate in this case. So I will just run it again so you can see these variations, which are related in this case with the presence of large crustal structures, again related to tectonics. So I think this is me. Thanks for your attention.
So thank you very much. Do you have any question for Manel? No? Yeah.
Manel, thanks for the talk. It was very illustrative. I really enjoyed the talk. And I'd like to ask you, you mentioned these subducting features. I was going to say seamounts, but in your work you mentioned about these reaches, and that those there are changes in rigidity associated to those subducting features that you interpret as the upper plate being more fractured. Am I correct?
Yeah.
Have you observed, for example, usually those fractures come associated with fluid flow, and I was thinking whether you see associated to these lower rigidity areas over the seafloor, areas of fluid emission, such as large pore mark concentration or mud volcanoes, or any feature that could be indicative of this fluid flow through these more fracture.
To my knowledge, there's no information about seepage, fluid seepage in the seafloor. But what we observe is in the seismic section that I didn't mention here are these reflectors over here. These reverse polarity reflectors that we interpreted in some areas, like here, over there, and there, as fluids. As sediment saturated fluids being transported. The point is that we argue that we don't really see reverse polarity reflectors in this area. So our interpretation is that fluids are escaping, but we have no information on the seafloor about this seepage.
But these reflectors with reverse polarity are due to the subducting plate that carries sediment with...
Yeah, that's the interpretation.
Yeah. Another question? No?
Thank you, Manel. I'm discovering what you're doing here, so for myself. I have just a question because I didn't understand very well what you call tsunami earthquakes.
Yeah.
So what I understood that these earthquakes reach, the trench, but I would like to know if in the case of Tohoku, is it considered as a tsunami earthquake?
No, the point of tsunami earthquakes were classified based on several aspects. The main one was that they actually trigger large tsunamis for the moderate magnitude that was recorded for the earthquake. Actually, these earthquakes were quite dangerous. Now I think they are considered in the early warnings, but the problem with these earthquakes is that they actually had a magnitude that was lower than the threshold to actually activate the alarm. So when these earthquakes occurred, nobody was expecting a tsunami, but the tsunami was coming. And the problem with that is that they were occurring in the shallow-most part where they are depleted in high frequencies, and that is basically kind of like shapes the magnitude value a lot. No? How the value that you get is actually influenced by this depletion in high frequencies. Now, also these tsunami earthquakes are classified not only because of that, but also because they are nucleated. They occur very close to the trench. Now, the Tohoku earthquake was nucleated at 20 kilometers of depth, which is more or less like the 1995 Colima-Jalisco earthquake. So the Tohoku earthquake also had a huge magnitude, and actually it reached to the trench, but it's not classified as a tsunami earthquake because it doesn't really fulfill all these aspects as the tsunami earthquake.
Manel, well done, thanks.
Yeah.
Can I ask you on the observational part of this? You had a few slides there and panels there coming with tens of gigapascals in rigidity, and for displacement and even the uncertainties there, right? That it's a little bit, I don't know the paper, but it's a little bit strange pattern, just having small uncertainties on the very bottom by the time you get to 25 kilometers, and then opening up and closing to the surface. But and the same thing happens with displacement. You've got, in the case of Tohoku, you've got things like tens of meters in displacement uncertainty, if you will. I was going to ask you from the observational point of view, the state of you had like seafloor geodesy coming all the way down to the trench, to the fault. What's the state of that, and would that help?
Well,
and the same thing with the OBS, you know, not only from the geodesy point of view, but from the seismic point of view. If you had those running during the time of a big earthquake, would you be closing the chapter, or how well you know here the story, or, you know, where are you?
I mean, I'm not sure if I would be closing the chapter, but I think we would be narrowing down the solution. So the first question related to the uncertainty I want to comment. This is basically showing the distribution of properties that the authors actually obtained from different subductions. Now, the problem with that is that these values come from tomographic models. These tomographic models usually depict quite well the shallowmost part, but the deepest part is actually not so well covered. So there might be a bias here from the initial assumptions that these models take, which are probably most of them are the same assumptions. So there might be some certain variation in these values, but let's say that at depth, these physical properties are not expected to vary that much because you don't have that much fracturing as well, okay? Whereas if you go to the shallow portion, as we have seen in the different studies, each subduction in the shallow domain is completely different because you have other different aspects such as seamount subduction, accretionary prisms, and stuff like that that will make this distribution vary a little bit, okay? So this explains this, the long error bar in here and not so much in here. Now, going back to the geodesy question, I think, yes, if you're in Japan, the geodesy, seafloor geodesy is at the forefront of everything. I mean, they are actually now deploying a fiber optic cable to actually record and monitor the deformation of the upper plate during earthquakes and during slow slip and tremors. And the fact that if you have also OBS information, which in the Tohoku earthquake, there were some ocean bottom seismometers that actually captured this fault displacement and the seafloor displacement, that would certainly help a lot to understand how the upper plate deforms and if this is a function of the upper plate structure or there are other factors playing during the deformation. Not sure if I answered.
I think so, but if I can follow with that.
Yeah, go ahead.
So if you had sugar daddy coming here and telling you, you've got as much money I'm going to give you as you wanted to, what would you do? Would you concentrate on one single location? Would you do that, you know, globally? And what kind of studies would you do, and what kind of equipment or instrumentation would you use to close the chapter?
Yeah. Assuming that I have a lot of money, I would certainly go for, it's not passing, but I would certainly go for this region of the world, okay? And I would certainly go for Chile, and I would certainly go for Japan. And possibly, I wouldn't go for just one. I would go for few of them. Like I would go for with fiber optic cables and OBS, an array of OBSs. This is actually something that is proposed now. There's a consortium or let's say a group in the States that has actually called Subduction 4D, which aims at understanding far better these processes. And the idea is to actually deploy an array. It's called the mega array, and would combine not only offshore instruments but onshore. So we can actually combine how the deformation occurs in both sites and and not only seismometers, but fiber optic, active source seismic acquisition, so reflection lines and other observables. So that's the way to go, certainly, yes. But I wouldn't go just for one place, because as I said and I showed in this talk, each subduction zone has its own little feature, and as they say, the devil is in the details. So I think we need to actually understand several subduction zones to actually capture the overall process and isolate these small features from each subduction.
Yeah, Manel, just one question from my part. So, in order to summarize a little bit your talk, what is in your? I want that you comment. What is the value for you of this kind of seismic experiments in order to assess the active seismic hazards? In order to predict not when but where the earthquakes can occur in a specific zone.
Yeah, I mean, obviously we cannot predict when they will occur, but we can predict the impact of these earthquakes. So you can predict, in the case of a huge earthquake that breaks the whole megathrust, with these studies you can give information, preliminary information on how much fault displacement this earthquake would occur with a certain magnitude. No? So this certainly will actually help to predict how large the tsunami would be, and therefore if you know where the tsunami will actually impact in the coast, you can actually focus on kind of like preparing certain parts of the coast for this potential hazard. So I think preparedness is the basics for mitigation. If people know what to do at the moment that this hazard, this event occurs, then you will actually be able to save lots of lives, I think. Yeah.
Thank you very much. Yeah, no more questions? So I think we can finish this session today.
Okay, thank you. Mucho que hecho.